Today I will be delivering a lecture on network programming. And before jumping on to the lecture, just let me just give you guys
I'm sorry, you can go ahead again. Thank you.
okay. So you guys might have heard of networking, network programming. So basically, when you say that okay, we want to do some network programming, it means that writing a program that can communicate with other programs across a computer network. So we're gonna learn what is a computer network in the coming slides. So there are several issues that arise when doing this network programming, which you will never face when you are writing a simple and a single application program which does not involve any kind of network. So this lecture basically will give you an understanding, excuse me, of the basic IO services provided in the Unix IO system. And you will learn how to use these services to build applications such as web clients and the servers that communicate with each other over the internet. And you will also gonna learn some techniques for writing these concurrent programs, such as the web servers that can serve requests to the multiple clients at the same time. So what is exactly this, the network programming, and what is the backbone behind this network programming? So network applications, they're everywhere. Anytime you browse your browser, the web, or send an email or play an online game, so you are actually using you're interacting with a network application. So interestingly, surprisingly, all the network applications, they are based on the same basic programming models, having same logical structures, and they rely on the same programming interfaces. So every network application is based on the client server model. So they have got this client server transactions. And with this model, an application consists of a server process and one or more client processes. So the server process is actually managing all the resources, and it provides some service to these client processes by manipulating these resources. So let's take an example that we have a web server that manages a set of disk files that it stores and retrieves for the client. Similarly, an email server manages a pool file that it reads and updates for the clients. So basically, the fundamental operation in the client server model is the transaction, as you can see in the figure here. So the first step in this client server transaction is that basically the client process, it will send a request to the server process, requesting some particular service that the server process is providing. So for example, we have a web browser, and it needs a file, and it sends a request to the web server. So that's like the step one, the client is initiating a process. In the second step, we see that the a server receives the request, interprets the request, and then it will manipulate its resources in an appropriate way. For example, again, saying the same thing, we have web server, it receives a request from the browser. It will read a disk file. So that's basically it's handling the request and doing appropriate action against the request received. And then on the third step, then after handling the request and doing the necessary action against the request, server will respond to the client, and it will send a response to the client and then waits for the next request to be served. So again, a web server that sends a file back to the client and then waits for the next request. So the last step is actually that the client receives the response and then manipulates it. For example, after a browser receives a page from the server, or a file from the server, it displays that screen or the file on your screen, right? So this is basically the whole this client server transaction model that almost every network application is having on the back end. The client will be sending a request, server will be processing that request, and then sending the response to that request back to the client, and then client is doing the necessary action on that received response. So this picture gives you guys an hardware organization of a network host, a particular network host. It's not the network like multiple hosts, it's just single host. So whenever you are interacting with client and servers, and they're often running on a separate host and communicate using the hardware and software resources of this host machine and the computer network. So basically, to host machine, just like you have CPU plugged in on your your system, you have USB controllers, you have graphic adapters, and they're all communicating through these IO buses. So you have this controller where your SSD or HDD is plugged in. So similarly, to a host machine, a network is just another IO device that serves as a source or sink for this network. So basically, it means that this network adapter is just an IO device that is being used for sending and receiving the data over the network. So, so what is exactly a computer network in real? So, in real, a network is a hierarchical system uh, which consists of bunch of boxes and in long wires. They are organized by a geographical proximity. So, this geographical proximity is important in a sense that it gives you a boundary, or it defines how your network is laid out. So let's say we have this SAN system area network. So it spans a cluster or a machine room. They're all, stitched together via this switched Ethernet, quadrix QSW switches, something like that, right? So this is a smaller scale network, system area network. And the second one is local area network, which you guys have even heard of, like LAN. It's very pretty common term that we use. So local area network spans a building or a campus. So, for example, we have Sogang LAN, across the campus, and this Ethernet is most prominent example of this LAN. So usually LAN is connected through this Ethernet, which can be 10 gigabit or maybe 100 gigabit per second. So similarly, we have this last one, the wide area network. So it's often referred to as WAN. It spans country or across the countries, and it has got typically high-speed point-to-point phone lines to enable the connectivity. So an internetwork, the term internet comes from this internetwork, and it is actually an interconnected set of the networks. So the global IP internet with an uppercase internet with an uppercase I is actually most famous example and implementation of this an internet works. So now we are gonna learn, or let's see how an internet is built from the ground up. So at the lowest level of the internet or this network, we have got this Ethernet segment. And Ethernet segment, it actually consists of some wires, usually kind of twisted pairs of wires and a small box called hub. As you can see, guys, in the figure, we have got hub, and there are three hosts connecting to this hub. So this Ethernet typically spans small areas, such as a room or a floor in a building. So each wire has got some maximum bit bandwidth. In this figure, we have got this 100 megabit per second. It can even span up to 1 gigabit per second. So one end is attached to an adapter on the host machine, and the second end is attached to a port on the hub. And each of these Ethernet adapter has a globally unique 48-bit address, which is stored in a non-volatile memory on the adapter. So adapter has got some non-volatile memory chip, so it can store this unique 48-bit address. And furthermore, a host can send a chunk of bits called a frame. So that's like a minimum unit that you are going to send, a packing unit, to any other host on the segment. So this is actually the unit of transfer between the segments. And note that this hub slavishly copies there's every bit that it receives on each port to every other port, so that every host sees every bit and frame, but the only destination host actually reads it. So hubs are on their way out. So bridges, switches, basically, and routers are becoming cheap enough so to replace them. So we're gonna see what is like this bridge and what is the role of these bridges. So this is the next level in the hierarchy. We've got this bridged Ethernet segments. So when we have multiple Ethernet segments, they are connected into a larger local area networks, LANs. So they are often referred to as the bridged Ethernet. So we have got in this picture, we have got this X and Y. So they are bridged Ethernets in this, they're acting as a bridged Ethernet. So basically, they are using a set of wires and small boxes called bridges. So bridge Ethernets can span entire building or campuses. So in this bridged internet, some wires connect bridges to the bridges. So and other connects bridges to the hubs. So the hub and the host we have seen in the previous slide. So we see that all the hubs, they can be connected to this bridge, and then there is an interconnection between the bridges so that this whole network can be connected. So usually the bandwidth of the wires can be different for each bridge. So for example, the bridge to bridge wire has got 1 gigabit per second bandwidth, while the four hub bridge wire have bandwidth of 100 megabit per second. So the bridges, they're very clever, and they learn using distributed algorithms to selectively copy the frames from port to port. So they've got this intelligent algorithms built inside. Okay, so in order to simplify these land figures, so we draw the hubs and bridges and the wires that connect them on a single horizontal line. So we just show the host, and then all the hosts are connected through a horizontal line. So we box all those bridges and the ports and the hubs, so that we just say, okay, all these hosts are connected to each other. So that's actually a conceptual view how people look at the LAN. So we don't show the Ethernet and Ethernet segments inward inside the pictures. So our next level in the hierarchy is internets. So the crucial property of an internet is that it consists of different LANs and WANs with radically different and incompatible technologies. Each host is physically connected to every other host. So for example, in this picture, you see that we have got this LAN 1, and it can have completely different and different technology. Similarly, we have LAN 2 on the right side. So it is called multiple hosts. They are connecting to this LAN. So all these hosts on the LAN 1 and LAN 2, they are connected to different routers, and those routers are connected to each other through this wide area network. So the thing is that this host on the LAN 1, the leftmost host on the LAN 1, can access or can communicate with the host on the rightmost LAN 2, irrespective, even if they've got this incompatibility and different technology, but they still be able to connect to each other. So this kind of connected area is called an internet. So this is actually the logical structure of an internet. So we have got these ad hoc internet interconnection of the networks. They've got no particular topology, and they're vastly different routers and link capacity. So every router has got its own characteristics, and it depends what kind of requirements are required. So people usually install those kind of routers and the switches in the way. And when you're sending the packets from source to the destination, for example, from the left to the right, so there are multiple hopes that a packet or the packet should go across, and these routers form bridges from one network to another. So we see that the host is making this a two routers connected. So one, we have got this one directly to the host, and the other one is going through a separate bridge, which is actually the bottom one. It's going to the right host again. So these different packets may take different routes, and you have so this is the structure that shows that how you have these bridges, and how those bridges, they are going to form an internet in real. So how is it actually possible? The question of the notion of an internet protocol. So why do we need an internet protocol? So what is the motivation behind this? Like, how is it possible for some source host to send database to another destination host across all of these incompatible networks? The solution, the answer to this question is that we have got this protocol software running on each host and router. The protocol software running on each host and router actually smooths out the difference between the different networks. And the software implementation implements a protocol that governs that how hosts and routers they cooperate in order to transfer the data. So this protocol actually provides different properties. We have got this naming convention and the delivery mechanisms. We are going to see how it works in the coming slides. So the key idea here is that the protocol gives you a thin layer that overcomes this data transfer between incompatible networks. So what does this internet protocol do? So it does two things for us. The first one is it provides a naming scheme, and the second one is it provides a delivery mechanism. So what is supposed to be the naming convention, or where does it stands for? So the different LAN technologies have got different and incompatible ways of assigning addresses to the host. So every host can connected to a different network can have a different scheme to give a name to the host or define the address of the host. So this internet protocol, it overcome these differences by defining a uniform format for host address. So you have got this uniformity across address definitions. So all the host addresses should be in a unique format. So this each host is then assigned at least one of these internet addresses that uniquely identifies it. So you have got this unique identification for that particular host in form of address. The second thing is that it offers a delivery mechanism. So again, the same different networking technologies have different and incompatible ways of encoding bits on the wires and of packaging these bits into the frames. So the internet protocol smooths out these differences by defining a uniform way to bundle up these data bits into discrete chunks. They're called packets. So packet is the most known unit that is being, that is used for transferring one small data bits to the other destination host. So what does this packet consist of? So this it has got two different properties. It has got a header and a payload. So a packet consists of a header which contains the packet size and the address of the source and destination host, and a payload which contains the actual database sent from the source host. So that's what the internet protocol do for us. So this is one of the important thing that you guys need to keep in mind when somebody asks you guys that, okay, what is internet protocol and what it does for us. So it gives you a naming scheme, it provides you a delivery mechanism. So this is the figure that shows that how the packets from one host, for example, in this figure, you guys can see host A and host B. So they've got two different LANs, LAN 1 and LAN 2. So how the data is going to be transferred from this host A on the LAN 1 will transfer data through a router to the LAN 2 host B, and it will use these encapsulation, so the packets will be encapsulated. So I hope you guys have some knowledge about what is the encapsulation. So basically you encapsulate a particular database or the payloads inside a particular abstract structure so that nobody can see it, or you can add some more generic headers on top of it. So the first step is that we have got this data from the client, and the client on the host A, it will invoke a system call that copies the client's data from virtual address space into the kernel buffer. And the second step follows is that the protocol software on the host A, then it will create a LAN 1 frame by appending an internet header and a LAN 1 frame header to the data. So we see that we have got this PH and FH, and this is the original data. Um, this the LAN 1 frame header is addressed to the router, and then it passes from the frame to the adapter. Notice that the payload of the LAN 1 frame is an internet packet, and whose payload is actually the actual user data. So this kind of encapsulation is one of the fundamental insights into this kind of internet networking. And the third thing is that the LAN one adapter, it will copy all those data frames, the packet to the network. So now the packet is in the network. So we have got this router LAN one adapter. It copies the data, and when the frame at the step 4, when the frame reaches out to the router's LAN one adapter reads it from the wire and passes it to the protocol software. So this horizontal line has got those Ethernet and Ethernet segments, but we are not going to show here, right? So to simplify, so we just made the figures like this. And the fifth step, what it's going to do is that the router fetches the destination internet address from the internet packet header. Like we've seen, the internet packet header has got this PH, has got that address of the host, destination host. So, and it will use this as an indexing into routing table being maintained by this router to determine where to forward this particular packet sent from the host A, which in this case is actually the LAN 2, because the packet is destined towards the LAN 2 host B. So the router then strips off the old LAN 1 frame header and prepends a new LAN 2 frame header here, and addresses to the host B and passes the resulting frame to the adapter. So similarly, like the step 5, the LAN 2, the router on the LAN 2 adapter copies the frame to the network. And at the step 7, we see that when the frame reaches this host B, its adapter reads the frame from the wire and passes it to the protocol software. So finally, the last thing is similar to host A, that the client data was copied from the kernel user address space to the kernel buffer, and then protocol software actually converted it. So similarly, on the host B side in the LAN 2, we see that the protocol software on the host stripes off the packet header and the frame header, and then protocol software eventually convert copy the resulting data into server's virtual address space when the server invokes a system call that reads the data. So we are ignoring a lot of, a bunch of important issues and questions. For example, we are glossing what if different networks have got this different maximum frame size, the packet differences. So due to these, there are a lot of segmentation issues that you can face when you're doing this network programming. And how do these routers, they know where to forward the frames, and how are the routers informed when the network topology changes? What if a packet gets lost in the mid or while sending due to some particular failure or due to some cable damage or anything? And there are several other questions. So all these questions and several others, they are going to be addressed by the areas of systems known as the computer networking. I think you guys have a separate course for that. So you will learn all these problems and solution to these problems in those classes. Okay, so we have seen that the internet was a common example of this global IP internet with the in uppercase internet. So this most famous example, and this global IP internet is most famous and successful implementation of internet, and basically it existed in one form or another beginning 1969. So it's still there since 1969. So it's not something new, but yeah, it's an example of this internet. So each internet host runs a software that implements this TCP/IP protocol. It's called the Transmission Control Protocol or Internet Protocol. So which is supported by almost every modern computer system. So this TCP/IP is actually a family of protocols, each of which contributes different capabilities. For example, this IP provides the basic naming scheme, delivery mechanism, like a sense. For example, this IP provides capabilities of packets datagrams from host to host. We have got this UDP, unreliable data protocol, and uses IPs to provide unreliable datagram delivery from process to process. We have got this TCP transmission control protocol, and it uses IP to provide reliable byte streams from process to process over connections. So these can be byte streams can be transferred process to process instead of rather than the host to host over connection. So and they all can be accessed via a mix of Unix file IO and the functions from the socket interface. So we will learn what is the socket interface in the following slides. So this is actually the hardware and software organization of an internet application. The socket functions they are typically implemented as a system calls that trap into the kernel and call various kernel mode functions in TCP/IP. So that's how the IO stack lays on the both client and the whole and the server side. So the client, we've got some user code, the simple application programs that are written for the networks communication. So we've got the socket interface. So the client application will call these system calls to invoke these socket interfaces, and then we go to the kernel. We have this TCP/IP, which will do further processing on these system calls and add some packet headers, transform those frames into payloads. And then we've got this hardware interface. It will use different interrupts to invoke this network adapter, and the network adapter will connect to the server host through this global IP internet, and the same way it goes up to the server. So that's actually the hardware and software stack organization of an internet application. So how they look like from a thousand feet view. So, how does a programmer looks at the internet, or what is the programmer's view on the internet? So, he sees that the hosts are mapped to a set of 32-bit IP addresses. So, we have got this, for example, 128.2.203.179, and the set of IP addresses that are mapped to a set of identifiers called internet domain names. So, for example, this IP that is mentioned above is mapped to a cs.cmu.edu. So, for example, we have discussed sogang.ac.kr. And the third one is that a process on one internet host can communicate with the process on another internet host over a communication, over a connection. So that's how a programmer actually, looks at the internet. That okay, it has got some address, it has got some domain name associated with, and there are certain service running on that domain name that can communicate with any other host or with any other internet host through binding or building a connection to this IP address. So apart from all those things, we have got two more things that are important. So we have got this IPv4 and IPv6. So some people often refer to as IP4 and IP6. And so the original internet protocol that was designed with it was a 32-bit address and is known as Internet Protocol version 4, the most widely used IPv4. So in 1996, the Internet Engineering Task Force (IETF) they have introduced this Internet Protocol version IPv6, so that they could have much more, space for the IP addresses. So it was 128-bit addresses, and it was intended as a successor to IPv4. But unfortunately, it wasn't very successful. And by 2015, by the end of 2015, so the vast majority of internet traffic or the users, they're still carried by IPv4. So only 4% of the users they access Google services using IPv6. They've got this IPv6 has got more security features, but it's not being used in real at the commodity users level. But yeah, maybe the big tycoons, these IT tycoons like Google's or Facebook, they might be using this IPv6. So in the rest of the lecture, we will be focusing on this IPv4, and but we'll also learn that how we can write some networking code that is protocol independent. So we do not have to specify that I'm going to access this IPv4 or IPv6. So we do not have to write different programs to different application programs to use this IPv4 and IPv6. Instead, the program should be this protocol independent. So, okay, the first one is IP address. So, an IP address is an unsigned 32-bit integer addresses which are stored in an IP address structure inside the system. So, it's nothing more than just a structure, data structure, which has got this unsigned 32-bit integer field. So these IP addresses are always stored in memory in network byte order. So they always use this big endian byte order. So a big endian byte order is basically means that the encoding starts at the most significant bit, and then you move in a descending order when you are doing the encoding for the rest of the bits. So that's why it's called the big endian byte order. So it is actually true in general for any integer transferred in a packet header from one machine to another. And the port number is always used to identify an internet connection. So you always need an address and a port pair to identify a particular internet connection on the network. Okay, so the IP addresses, if it's using a hexadecimal format, it's pretty difficult for humans to read, right? So so in order the IP addresses to make it more intuitive, so IP addresses are typically presented to humans in form of human readable format known as dotted decimal notations. So where each bit is represented by its decimal value and separated from other bytes by a period. So basically this full stop dot. So for example, this 128.2.194.242 is the dated decimal representation of the IP address. You can see like OX 8002C2F2. So this kind of hexadecimal number. So it has got this dotted decimal notation representation for this IP address. So it's pretty difficult to actually remember the IP on the left, so compared to this dotted representation. And similarly, the people have been using this get address notification, address information, and get name information functions, which are going to be converted later between which you can use to convert between the IP address and this dotted decimal. So it works in both ways. So you can convert from IP address to the dotted decimal, or you can convert from dotted decimal back to the IP address. So these two functions are very important, and we are going to see how they actually work and what is the script inside these functions. Okay, these internet domain names. So we have been moving up in the hierarchy. So now we have reached up to the internet domain name. So this hierarchy is represented as a tree, the internet domain name hierarchy, and the nodes of the tree represents domain names that are formed by the path back to the root. So you always move back to the root, and the root is like the top hierarchy. And the next level is a collection. The first level is actually the collection of first level domain names that are defined by the non-profit organization. So I think it's called Internet Corporation for Assigned Names and Numbers. So it's called ICANN. So the common first level domain names include edu, gov, com, .org. For example, in Korea, I think it's like .ac.kr. And then at the next level are the second level domain names such as emu and emu.edu. So we have got the sogang.ac.kr, so which is assigned on the first come first serve basis by the various organizations of ICANN. And moving from the third level onwards, like fourth, fifth level, so the organization is free to create its own third level domain names and fourth level domain names. For example, we've got this cse.sogang.ac.kr. So that's like the third level of the domain name. And there are multiple other domain names. The mechanical department has got its own initials in the domain name. So organization is given privilege or given a freedom so they can create their own third level domain names. So there is no bound from the ICANN organization to have these domain names at the third and fourth level. Okay, we have got these domain names, but who is managing all these domain names? So for that, we have got these domain naming systems. So internet is maintaining a mapping between IP addresses and the domain names in a huge worldwide distributed database called DNS. So we see the DNS, but we never know that what does it mean. So it's actually a domain naming systems, and there's a big, huge distributed database running behind the internet, and it is having this mapping between the IP addresses and the domain names. So conceptually or logically, a programmer can view the DNS database as a collection of millions of host entries, whereby each host entry it defines the mapping between a set of domain names and the IP addresses. And in mathematical notations, a host entry is an equivalence class of the domain names and IP addresses. So every host has got a multiple, maybe it contains like thousands or hundreds of these domain names and IP addresses associated with that host entry. So the characteristics of these domain naming systems are DNS mappings. So basically, they lets you explore. You can explore the domain name and the host using this NS lookup. So output is edited for brevity. So for example, each host has a locally defined domain name, localhost, which always maps to the loopback address or the local IP, we always call it. So if you write this in your terminal, ns lookup, name system lookup, localhost, then it will always return you this local address, 127.0.0.1, or some people call it loopback address. So it's just multi different names for the same IP. And if you type this host name, then it will give you the real domain name of the localhost, basically the what is the domain name against this IP registered. So we have got these multiple, scenarios. So, for example, in the simplest case, on the first bullet, you see there's a one-to-one mapping between a domain name and an IP address. So, if you do this NS lookup and you type in some domain name, then you will get some single IP. And in the second case, we have got these multiple domain names mapped to the same IP address. So, for example, you see that if we are looking up this ns lookup cs.mit, and in the second case we are doing lookup in ns lookup eecs.mit, we are getting the both same ip as output to these commands. So this is also a case when your multiple domain names are mapped to a same ip address in the dns. And in several other, I must say that in majorly being used is that we have got multiple domain names mapped to a multiple IP addresses. So there's a set of IP addresses that are being mapped to a particular IP domain name. So for example, we have got this twitter.com, and it has got these multiple IP addresses associated with it, are mapped to it. So and moreover, so we see that sometimes there are multiple valid domain names. They are still not mapped to any IP address. So if you do type this nslookup and ics.cs, so this domain name is not yet mapped to any of the IP address. So it might be done by the organization, or maybe they never use this domain name. Okay, moving on to the internet connections on this part. So, internet clients and servers, they communicate by sending and receiving streams of bytes over the connections. So we have seen a lot of things in the IO stack. They've got this protocol, Ethernet segments, and then routers. So a connection is actually a point to point in a sense that it connects and it connects a pair of processes. It has got different properties. It's a full duplex in a sense that the data can flow in both directions at the same time simultaneously, and it is reliable in a sense that bearing some failure, such as a cable cut by the QoS operator who's managing those cables. The stream of bytes sent by the source process is eventually received by the destination process in the same order it was sent. So this is quite important. This reliability property that we have been sending a stream of bytes from the source, and they should be received at the destination in the same order the way it was sent. It shouldn't be in order that okay, we are sending packet 10, packet 9, packet 8, when they should be receiving between in a different order. So a socket is an end-to-end point of connection, and the socket address is actually always defined as an IP address, colon this port number pair. So it's actually a pair IP address and port. And each socket is got its corresponding socket address, and it consists of an IP address and a 16-bit integer port and it's noted by the notation address and port, so it's actually a pair. And the port is the client's socket address, which is assigned automatically by the kernel when the client makes a connection request. It is known as an ephemeral port. So ephemeral port is which the client, when client wants to request a server, so the client IP address will be appended with an port, but the user won't be able to see this. So it's called an ephemeral port. And there are several well-known ports. So, for example, if you're using some service provided by server, port 80, for example, port 80 is associated with web servers. So we're going to see what kind of well-known ports they are associated with, what IPs or what port numbers. So well-known ports and service names. So they have been permanently assigned well-known ports and corresponding well-known service names. For example, this eco server running on your system, it's got this 7 port number. If you're running SSE server, it has got this 22 port number. We've got this email server, it has got this SMTP server running, then it's got this 25 port. And if there is HTTP server running on like a web service, they've got the 80 port number. So mapping between these well-known ports and service names, they're all contained in the file slash etc slash services on each Linux machine. So you can go and check, this cat etc service file, so you can see what are the port numbers they're mapped to what services. So, okay, what is an anatomy of a connection that we have been talking all along the the lecture starting from the beginning? Okay, we are going to build a connection. So, what does the connection looks like when we open or unbox this um, connection thing? So a connection is uniquely identified by a socket address of its two endpoints. So this pair of socket addresses is known as a socket pair and is denoted by a tuple as shown here in the slide. In the second bullet, we have got this client ADDR, client address and client port, and we have got this server address, and colon server port. So we see that two clients, they need a socket pair, and client and server, in order to communicate they need a connection socket pair. So that connection socket pair must have the IP addresses and the port for both sides, the server and the client. So for example, in this case, as the picture shows, on the client side, we see that there is a port 51213. So it's actually an ephemeral port, and it's allocated by the kernel and not by the user or the programmer who wrote that program. But on the server side, we see that this 80 port is appended, so it means like it's a well-known port and associated with the web server. So the person who programmed the server, he explicitly mentioned this port number. Okay, so using ports to identify the services, it is pretty important that when you have client and server socket addresses, the connection between these two is identified by the socket pair and port. So, for example, if a single host is running multiple services, then that a server needs to be appended with a particular port number in order to request a particular service from that server. For example, if you see this figure, we have got this connection between a web client and a web server. So the client host sends a request to the server with the port 80, so where this web service is running. So we see that there is another service running on this one with the eco server on the port 7. So if client wants to send a request to this eco server, he should append this 7 in the request, so that it the key beauty of the port here is to show that, okay, if you have multiple services running on the same server or in the same host machine, then you need to explicitly identify the port numbers or append the port numbers in the IP address so that you can access these services. Okay, we have seen the socket connection and socket. In order to build this client server communication, you need a socket connection pair. But what does a socket interface provides? Socket interface is a set of system level functions that are used in conjugation with the Unix IO to build these network applications, and it has been implemented on most modern systems. So it was created in early 80s as a part of the original Berkeley distribution of the Unix that contained an early version of the Internet protocols. And it is available on all the modern systems. So we've got this Unix variants, Windows, OS X, Android, Macintosh, and all the machines they've got this socket interface. So diving deep inside the socket, what is it, a socket? To a kernel, how the kernel sees a socket, it's actually a socket is an endpoint of communication. So an application to a kernel, okay, it's an endpoint of communication, but to an application, a socket is a file descriptor that lets the application read and write from or to the network. So basically sending or receiving the data from or to the network. So, but a key point to note here is that you guys need to remember this thing. That all Unix IO devices, including networks, they're all modeled as a file. So your Linux machine or Unix machines, they will be seeing your devices as a files. So these client and servers, they communicate with each other by reading from and writing to the socket descriptors. So we see that we have got this client file descriptor and the server file descriptor. So they both have got these descriptors at their end. And in order to communicate, you need to either read or write to this client FT and the server FT. But there's a small distinction between the regular file IO and the socket IO is that how application is going to open the file descriptor. In regular files, the file you just open the file using these file descriptors, but in case of these socket file descriptors, so they have got like different mechanism to open them. Okay, so how does the socket is addressed or identified, and what is the structure that it uses? Sorry. So the generic socket address, the connect, the bind, and accept functions, they require a pointer to a protocol specific socket address structure. So basically, the file descriptors of the server and the client, they work like you have to call some connect function, a bind, and accept function on the server side. So that it requires a pointer to a protocol specific socket address structure. So that socket address structure, initially the problem faced by the designers of this socket interface was that to show how to define these functions to accept any kind of socket address structure in order to overcome the incompatibility and different technologies. So today we would use this generic white pointer, which did not exist in C at that time. So their solution was to define socket function to expect a pointer to a generic socket address structure. So for casting, for explicit casting convenience, so they adopted this Stevens convention. So type defines socket address structure. So we're using whenever you are using this Stevens socket address structure, so you must explicitly cast to this from socket address in pointer to socket address pointer, so that the functions that takes the socket address as an argument. So we've got this socket in family, socket in port, socket in address, and this socket in network in zero, so that we can have some padding to the to the size of the socket address. If your socket address is smaller, so you can pad a lot of zeros at the end. So this figure gives you an overview of the interface in context of the typical client and server transaction. So we see that we've got this a client and a server, and this the whole IO stack and how they communicate with each other. So the first time we see that the server will start. So we need to initialize our server, and once the server is running, so it has got a lot of methods, which is like socket bind, socket listen, socket accept, and get address information. So once our server is up, then the next task is that we uprun our client, and we will start the client. And then client has got only two method. We've got this get address information, and then it connects to socket, and socket has this connect function. So connect has got send to the client, to the server. So once the connection is accepted by the server, Then the client server session starts and they can exchange the data on the third step. So and meanwhile they are exchanging the data, server is also awaiting new connection requests from other clients, so that there can be multiple other clients they want to connect to the server, this server from the same client to accept more requests. So once this exchange of the data has occurred and we are done with the operation or the request, and so client received the request, then the client will disconnect from the server by calling this close function, so end of file, and the server will release this client, and it will drop this client, and that's the whole operation. So we see that this is the common function in both client and server, this get address information. So the arguments to this socket connect are generated from us by this get address information method, and which allow our codes to be clean and portable. So it's a pretty pretty good function, and we do not have any kind of it lets us not to define any kind of hard-coded IPs or the addresses or the host names. It brings up all the information that we need to hook our socket structures, so that our socket addresses are able to connect, or they're able to accept and listen and bind addresses. So okay, we have got this host and service conversion. So we use this get address information. This get address function and the socket interface can seem somewhat kind of daunting when you first learn about them. So the get address information is the most modern way to convert string representations of the host names, host addresses, ports, service names to socket address structures. So you replace these. They were replaced. Actually, this get address information replaced these obsolete get host by name and get server by name functions. So previously, people used to invoke these get host by name and get server by name from methods, and there are certain advantages of using this get address information, that it's more like a re-entrant and can be safely used by the threaded program. So you don't, it's a thread safe, so you do not have to worry about when your application, your program is complex and multi-threaded. And second thing is that it allows us to write portable protocol independent code. So it works with both IPv4 and IPv6. So we have seen in the initial slides that, okay, we will learn how we can do this protocol independent network connection building. So actually this is one of the key things that you use get address information to build the protocol independent source code for your network application. Somehow there are actually trade-offs. It's like a disadvantage that it's somewhat complex compared to this get host by name and get server by name methods. And another disadvantage, maybe it's like, fortunately a small number of usage patterns suffice in most of the cases. So you do not have to really go for very complex cases. So even a simplified use case suffice your application needs. So so moving further inside the get address info method, we see that we have got these like four parameters. We have got this host name or address pointer, we have got this port or service name, and we've got these input parameters like hints, and we've got this result, which is actually a linked list, which is returned back when somebody hooks this get address information. So we will see what is the linked list, and we have got this. There's a couple of other methods that we can call free address information. So it's basically like you free the memory in C. So it's like something similar. So it frees up the linked list. And similarly, we have got this error conversion methods, GISTR error. So it converts, returns the error message to the client or to your application program. So given host and service, it results the point that point to a linked list of address information structure, and each of which points to a corresponding socket address structures, which contains arguments for the socket interface functions. So there are two helper functions, as I've already explained here. So this is actually the linked list returned by the get address information. So given host and service, the two components of a socket address, So this get address information returns a result that points to a linked list of address information structures. And each of these points to the socket address structure that corresponds to a host and a service. So once a client calls this get address information, it walks this list. So trying each socket address in turn until the calls to the socket and connect succeed and the connection is established. Similarly, on the server side, each socket, because we have seen that both client and server, they call this get address information in the picture a couple of slides back. So the server, similarly, this in the same patterns, the server tries each socket address on the list until the calls to the socket and the bind succeed, and the descriptor is bound to a valid socket address. So open sock FT, it's like open socket file descriptor. So all these um, things happen through this get address information structure. So this address information structure, it has got these hints, the first argument to each function, family, the socket type, this protocol, this canonical host names. We've got this address information, address, and the pointer to the next item in the linked list, because the linked list, so it has got like this moving forward links on the node. So each address information structure returned by this get address info contains arguments that can be passed directly to a socket function, and also points to a socket address structure that can be passed directly to the connect and bind functions. So now talking about the get name information, not the get address information, but get name information. So actually it's an inverse of get address information. So it converts a socket address to the corresponding host and service. It replaces the obsolete get host by address and get service by port functions. So it has also got these advantages over the get host by address and get server by port. Basically, it's also a re-entrant and it's protocol independent. And re-entrant means like it's a multi-threaded safe program, so you can just hook up in your complex multi-threaded network applications. So the structure, this method also takes this socket address input, and we've got these two host length and service. They're like different pointers that we use, and we can also use certain flags in form of integer. So let's see a simple program that calls this host information to get the address information and get host name to display the mapping of a domain name to its associated IP address. So at first we initialize the hint structures as in the figure here you see hints.ai family and hints.ai socket type. So the hints structure so that the get address returns the addresses we want. So we want this AFINet, we want IPv4 only IP addresses, and we want only the connection. So we will hook this get address information. And after we are done with the call to the get address information, then we walk up the list of address information structures using this get name information. So the method that we have recently seen to convert each of the socket address to a dotted decimals address representation format. So after walking the list, we are careful to free it by calling the free address information. So the helper method that we have seen in the couple of slides back. So although for this simple program, it is not strictly necessary to call this cleanup free address information, but in more complex programs, I think it's a very good practice to call your free address information. So it will, free up all the linked list addresses um, that have been retrieved using this get address information. So next, we are going to run host information so we can see the IP address running behind. So we see if we type this host information, the program that we have recently seen, the script, the snippet of the code. So if we run that, so we see that if we type like host info and the local host, we will get this loop IP address, the loopback address, the local IP. Similarly, if we type some domain name against it, so it will bring back this IP, and actually the IP is converted to the decimal representations for easy readability. So if you're running a host, um, so it's just the case where multiple IP addresses there, so set of IP addresses they are bind to a particular domain name. So we see if we run this one, we have got these multiple information here. So the output will be like multiple set of IP addresses against the domain name registered. So these are all things coming from the domain naming systems. Okay, folks. Thank you so much. That was it for today in my lecture. So next time you will be, learning of using this get address information for host and service conversions in further detail, and you will learn about writing client and servers, and writing your own web servers. And I think that will be covered by Professor Youngji Kim. So that was it for today from my side. And if you have got any questions, please feel free to ask me right here, or I will ask Jungkook to post my email on the e-class, so you can even ping me on email.
Uh, always thank you for presentation.
Right.
그 퇴장해 주셔도 되고 박사님 각 그 프레젠테이션 준비 되게 고생해서 하셨으니까 고맙다고 한 번씩만 말씀해 주시고 퇴장해 주시면 감사하겠습니다.
Thank you for the lecture.
Thank you. Okay, Jungkook, I think you can wind up if you want to. Maybe do some
Uh,
stuff. You can just wind up here.
okay, thank you again for the presentation,
Yes, thank you so much.
and I will contact you later.
All right.
Okay, thank you a lot.
Thank you. Bye.